apply trajectories. Professor Taketsugu.
Yes. Thank you for introduction. I'm Tetsuya Taketsugu from Hokkaido University. And it is a great honor for me to give a talk in this worldwide quantum chemistry symposium. I would like to thank the one of the committee, especially Professor Choi, for inviting me. Today I will talk about visualization of reaction path global reaction route map and on-the-fly trajectories. So first, let me introduce myself. I am a member of GAMES family, and I joined as a postdoc in Mark Gordon Group in ISU 1994 to 1995. And at that time, I implement on-the-fly molecular dynamics code in games. In e-games, this code, this option is called dynamic reaction coordinate. And later, I joined the Kimiko Hirao group as assistant professor. And at that time, I work on vibrational self-constant field calculation directly linked with games. And this code was also implemented in games and with my colleague, Dr. Kiyoshi Yagi. He was actually at that time a student. So my research field is potential energy surface and vibrational state calculation and reaction dynamics. So not electronic structure calculation code. But from the output of electronic structure calculations, we can get the information on potential energy surface, and especially for chemical reactions, the reaction path concept is very important. And also from vibrational state calculations and reaction dynamics following based on this potential energy surface. And my colleague Satoshi Maeda developed a very interesting methodology, global reaction route mapping. And he developed the software, also GRRM, which can explore all the reaction pathways on the potential energy surface. And as for vibrational spectroscopy, my colleague Kiyoshi Yagi developed harmonic state calculation software, Shindo. Shindo looks semi-empirical molecular orbital method, but actually Shindo has a meaning of vibration in Japanese, so he named it Shindo. And in our group, we developed the on-the-fly molecular dynamics code. And especially the target is excited state dynamics with surface hopping scheme. And I employ Tari's Hughes-Stich's algorithm. And recently, we also implement in Zhu Nakamura algorithm. And also recently, we implement the classical multidimensional scaling scheme to analyze reaction pathway and reaction route map and on-the-fly trajectories. So, sorry. So the basic concept, reaction path, is introduced by Fukui, Nobel Prize, intrinsic reaction coordinate. So IRC is defined, uniquely defined for elemental reaction in mass-weighted coordinate space. And the definition depends on the tangent vector. Tangent vector is a potential gradient. So once the IRC pathways is determined, we can calculate the vibration frequency modes along the IRC. Then we can get the 3n-6 dimensional reaction path potential energy surface. So by applying a harmonic approximation to vibrational modes, orthogonal to the reaction path. So this potential curvature can change along the IRC pathway. Then Miller, Handy, and Adams developed formulated reaction path Hamiltonian. So this shows this part corresponds to the reaction coordinate motion. And this part corresponds to bidirectional coordinate motion. And IRC pathway is a curved pathway in multidimensional coordinate space. So this curvature invokes the coupling between reaction coordinate motion and bidirectional coordinate motion. So in this formula, BKL and BKS correspond to the curvature coupling. So if the molecular system proceeds along the IRC pathway, so this is a highly curved region, then molecule has a momentum, so it feels centrifugal force. Then it leads to bidirectional excitation. So curvature is an important factor in dynamics. And the second important factor is bifurcation. So this shows illustration for CH3O, mesokis radical, and hydrogen move from carbon to oxygen within the molecule. And as shown here, transition state has a CS point group. And the IRC keeps symmetry of the molecule. So the termination of this IRC also keeps CS symmetry. And this corresponds to second transition state. And it connects to symmetry reduced minima. And in this case, the potential surface feature changes from Barré to ridge at some point. So we call it the Barré-ridge transition point or Barré-ridge inflection point. And lambda, potential curvature lambda, changes its sign from positive to negative. So at this point, lambda becomes 0. And this is a symmetric case of bifurcation, but in general, it can occur for asymmetric case. So from minimum and transition state, and IRC is connected to one minimum. But sometimes Barré-ridge inflection occurs along the IRC. And actually, IRC calculation cannot find this hidden minimum. But actually, there exists some pathway. So IRC is very important and significant concept, but IRC doesn't consider the dynamics effect, curvature, and bifurcation. And Hasse and Crockers proposed non-IRC pathway is important in the actual reaction. In 2002, they published this paper in Science, and the target reaction is SN2 reaction. And OH minus attack CH3F from backside. And the product of SN2 reaction is just fluorine anion atom depart from the moiety. But the IRC calculation indicates the terminal of this IRC is not dissociation product. This is this one. This is a terminal product of the IRC. So fluorine atom start to rotate around the moiety, and it is bound to OH bond. Then recently, we developed the method to visualize the IRC pathway in reduced dimension. So this is a movie of structural transformation along the IRC. So first, fluorine atom try to escape, but it rotates around the moiety, and it is bound to OH. And this is the energy profile. And this system has 7 atoms. So 7 atom system, internal degrees of freedom is 15. So this structural transformation can be described in 15-dimensional coordinate space. But we applied this CMDS method. This is actually principal coordinate analysis, the same. Then we can extract the important coordinate. And actually the input is geometrical information. So in this case, we choose 101 geometries along the IRC pathway. And then we evaluate the distance between the structures. So from this distance matrix, we can get this principal coordinate information. And this is a weight of the respective coordinate description. So actually, this IRC can be mapped on 2 dimensions. And the 2-dimension description, the percentage is 95%. Okay. The next, we have interest to draw on-the-fly trajectory in this subspace. Actually, CMDS, by applying CMDS only IRC, first we can determine principal coordinates. And then trajectory data out of sample data. Then we can use out of sample extended CMDS methodology. Then we can put the trajectory information in the same 2-dimensional subspace. Actually, we run 50 trajectories, and 20% trajectories proceed along the IRC, and 80% lead to dissociation, SN2 reaction pathway. So as you see, the trajectory depart from the IRC along the highly curved region. This is because the molecule feels centrifugal force in this direction. But in this case, the IRC attracts the molecule to the IRC again. Then it comes to this region. But in this case, the molecule leave from the IRC like this. So Hase et al. Perform the trajectory on-the-fly trajectory, and actually they reported 90% leads to SN2 dissociation, and 10% lead to IRC terminal. Our results are qualitatively agreement with their result. And next, we want to go to the next stage. This is a global reaction route mapping strategy. And this strategy has been proposed by Maeda, Ohno, and Morokuma. And actually, they developed 2 methods: anharmonic downward distortion following method, ADDF, and artificial force-induced reaction method, AFIR. These 2 methods can find the transition state from bottom of the potential surface, or by adding artificial force. Actually, okay, we explain that respectively. So in the ADDF method, we want to locate the transition state, which are connected from EQ. And based on the unharmonicity of the potential energy surface, ADDF method can find the direction which leads to transition state. So in this case, 4 ADDF paths are generated from one potential minimum. And AFIR method, this is a normal potential curve for reaction. A plus B becomes AB. So there is a barrier, there is a transition state. And in this method, artificial forces put to the molecular system. Then the potential energy surface change. And actually, as shown here, transition state disappear, barrier disappear. And based on these functions, we performed only geometry optimization starting from this. Then we can get the information of this pathway. Then we can get the good guess for transition state. By employing these two methodology, for example, we can get the global reaction route map. And this is a case of C4H6. 100 minima, so very small, but circle correspond to minima. And 400 transition state, square marks correspond to transition state. And this is actually very complicated. So I show the more simple way, simple global map. So this is application to gold cluster, gold 5. And by employing ADDF method, we can get 5 minimum and 14 transition state and 5 barrel-rich transition structure. And they are connected like this. So this line corresponds to IRC pathway. Actually, in this reaction system, we can locate a barrel-rich transition point also. And this is global minimum. So this structure very symmetric. So C2V point group, and the 9 IRC pathways are connected. So starting from minimum, 1, 2, 3, 4, 5, 6, 7, and 9 transition states are connected. And this double line indicates this transition state corresponds to the transition state which connect to minimum. So this is gold cluster, the same gold atom, 5 gold atom make this molecule. So 2 gold atoms are exchanged. This is also reaction. So this double line indicates the IRC for exchange of 2 gold atoms. And so now we can get the map. Then next we want to consider how the dynamical trajectory move on this map. So to map the trajectory information over this IRC network, we propose a method to map to do this. So this is procedure. So first, we make global reaction route map for a given system and choose reference structures from the IRC network, like this. Then we run trajectory, on-the-fly trajectory. For a given point on the trajectory, we evaluate the distance from all the reference points, like this. And the definition of distance is this. So x traje t is 3n dimensional mass-weighted Cartesian coordinates at time t. And xi IRC is also 3n dimensional mass-weighted Cartesian coordinate for ith reference point. And we fix the center of mass to the origin. And also we determine the orientation of coordinate axis to minimize this function. Then we plot variation of distance as a function of time like this. Then we can determine the closest reference structure. Then this figure informs us the trajectory's location is close to which reference structure. And this is the result. So starting from TS11D, this is 3-dimensional structures, and the relative energy is a little bit high, 20.8 kilocalorie per mole. We run the trajectory 200 trajectories. And 86 trajectories directly reach the mean one. But 114 trajectories go to other transition state, other TS1, 3, 1, 4, so many transition state. And also 62 trajectories are dominant, so it go to TS13A. And this is a summary of deviation of trajectories. So most trajectory first lead to VRT1, but 86 lead to mean one, but other trajectory go other regions. But we should consider the meaning of map. So if map, so this is a map for minimum and transition state. And in the global reaction route map, the location of mean and TS is very important. Should be determined to reproduce mutual distances as much as possible. So we apply CMDS, and yeah, actually this system, 3 dimensions are important. And yeah, in 2 dimensions, we put each reference point. And this is a handmade map. First, I show this. Actually, this shows only the connectivity information. But this is a result of map generated by CMDS. And now we understand why the trajectory from TS11D go close to the TS13A. And actually, we can eliminate the high energy structure and low energy regions. We can make a reduced reaction route map. So this involves TS11D, the mean one, and TS13A, and perform the trajectory. And actually, so this trajectory proceeds along the IRC, but it attracts to TS13A once, and it leads to mean one. So now we can find interesting feature, IRC jump. So trajectory can jump or hop from one IRC to another IRC. So now I summarize. So analysis of on-the-fly trajectories on the basis of global reaction route map consisting of IRC pathways can provide understanding of reaction dynamics from mechanical viewpoint. So key concept is reaction path curvature, bifurcation, jump. And the CMDS and out of sample CMDS are good tools. Okay. Finally, I acknowledge my co-authors. So Mr. Takuro Tsutsumi, he's a main player in this research. He's a PhD student. He will get a PhD degree soon. And Dr. Yuriko Ohno, and this is our group member. Okay, thank you very much for your attention.
Thank you very much, Professor Taketsugu. Okay, I still don't see any questions on the chat window. Any other? Oh, okay. Dr. Sebastian Mai, go ahead.
So Professor Taketsuga, thank you for this nice presentation. I have a question to how you map this this route map, and this is related to spatial symmetry and permutational symmetry. So how do you treat this? Because you said that there can be many different minima that just differ by symmetry, by exchange of atoms.
Okay. Okay, thank you. So actually, this is gold file. So 240 nuclear permutation inversion isomers. And depending on the point group of the structures, this never change. And we calculate all the patterns, all the distances, and we choose the smallest distance. Okay. So if we distinguish these isomers, we can discuss this kind of analysis. So actually, this mean one are connected, and this is actually change of gold atom, the same structure. By distinguish these structures, we can draw this kind of pictures, and also we can apply CMDS or OCMDS. So we can choose. That's okay.
Okay. Yeah, looks good. Thank you.
Thank you.
Okay, does that answer your question? Okay, any other questions here? Oh, okay. Elfie Krakow, please go ahead. Okay, Elfie, go ahead. Let me see. Okay. Okay, Michael. Okay. Yes.
There are many organic reactions which proceed without a barrier, which doesn't mean that they don't have a mechanism. And so is there a way to generalize your methods to other paths than IRC paths, which of course require a transition state?
Your question is, so in organic reactions, the mechanism is...
Yeah, if I have a reaction which proceeds without a barrier.
Out of barrier.
Then I could, for example, envision a path which just goes uphill. Not an IRC path, another general path.
Another general path? Okay.
Yeah.
So we can generalize, not only restricted to IRC. So once we determine the reference pathway, we can choose the reference structures.
Yeah.
And determine, so applying CMDS and determine the coordinate space. And the trajectory can be mapped using OCMDS. And based on this pathway, your suggested pathway, we can generate.
Yeah, thank you very much.
Thank you.
Hey, great. Any other questions?
There's another person waving hands. Let me allow to talk.
Can you hear me?
Yes, yes.
Great. I really like the talk. I wasn't aware of this method before, and I find it very interesting. Anyways, if I understood correctly, all of these dynamics calculations were run using direct dynamics, on-the-fly dynamics. Have you considered using fitted potential energy surfaces? There are quite a few good ones nowadays.
Yeah.
I mean, we can run millions of trajectories on fitted surfaces.
Yeah, so actually computation cost increased, but so not on the fly, but you use fitted potential surface, and you can increase the number of trajectories, and we can also analyze the same. So first we determine 2 or 3 dimension, then many trajectories mapped on this dimension, reduced dimension. Then we can discuss the dynamics. Okay.
Okay.
Thank you.
Okay. So I guess